In this video, we discuss the fourth isomorphism theorem. Now we will state the fourth isomorphism theorem. Let n be a normal subgroup of G. Now we're going to find this script S of H and G for two groups H, a subgroup of G, to be the set of all subgroups K that are between H and G. This is just a general notation. Then the fourth isomorphism theorem states that there is a bijection between the collection of subgroups between n and G and the collection of subgroups between the trivial subgroup and G mod n, where here n is a normal in G, and obviously you need this fact in order for G mod n to even be a group. And then what is the proof? Well, one obvious thing is to take a subgroup here and to mod out by n. And what do you need to check? You need to check that n is in fact a normal subgroup of H. If that's true, then H mod n is in fact a group, a subgroup of G mod n, containing the trivial subgroup. And so then this is in fact a function. Of course, this is not that hard to show. Why? Because, well, what do you need to do? You need to conjugate n by elements of H and see that you get n back. But guess what? This is already true because H is an element of G. And you're already assuming n is normal in G. That is, given an element in H, it's also an element in G. Since n is a normal subgroup of G, by definition of being normal, H inverse NH is equal to n. Therefore, it's true for every element in H. Therefore, n is a normal subgroup of H. So that allows us to conclude that this equation, this formula, actually does in fact define a subgroup in this codomain. So this is a function from this collection to this collection. So now we just need to prove it's a bijection. First, let's show injectivity. Suppose phi of H is equal to phi of H prime. Well, then that means H mod n is equal to H prime mod n. Well, let's take an element in H. Well, then this coset H mod Hn is an H mod n. It's also an H prime mod n. So we have this coset with representative little h is an element in H prime mod n, which means that it also has a coset representative that's in H prime, little h prime. By definition of equality of cosets, this means that little h is in the coset little h prime capital N. Hence, we can factor little h as little h prime times little n prime for some little n prime in n. However, since n is a subgroup of H prime, these two elements are both in H prime, so their product is in H prime. Right? Because this means that n is also in H prime. And so H is an element of H prime. So we started with an arbitrary element in H, and we showed it's an element in H prime. Therefore, H is a subset of H prime. Now you can go through this proof again and delete the primes where you have them and put them where you don't. And you'll discover that H prime is also a subset of H. And so, in fact, these two sets are equal. And so this map has to be injective. Now, why is this map surjective? Well, let K be a subgroup of G mod n. Note what this means. This means that K is a collection of cosets that's closed under multiplication and inversion. And the identity element what seems like the most natural thing to try is to let H be the collection of elements that appear in any one of these cosets. So G is Gn. Yes. Any coset, any element that's a coset representative of one of the cosets, or equivalently, the union over every element in every coset in the collection. Well, what do we need to show? We need to show that N is a subgroup of this H we just chose. Well, let N be an element in capital N. We need to show that N capital N is an element in this collection in the codomain. But N capital N is the identity coset. And we're assuming K was a subgroup in G mod N. And subgroups always contain the identity element. And so N is an element in K. Ergo, since N is an element in K, little n is here. We see little n is in K. And so by our definition of H, we see that we get this correct definition. For every element in N, we see this corresponding coset is in K. So every element in the normal subgroup is in H. That works. Now let's show that H is in fact a subgroup. Let G and G prime be elements in H. Well, then we want to show that the shortest version of the subgroup property works. We want to show that G inverse G prime is in H. Well, what does that mean? We want to show that G inverse G prime times N is an element in K. That's not too hard to show because this factors as G inverse times N times G prime times N. Well, this first factor is just the inverse of this coset, which is already an element in K. And this one is also an element in K, both by assumption because G and G prime are elements of H. And that's the definition of H. But K is a subgroup, so by the subgroup criterion, since these two elements are in K, the inverse of one times the other is also an element in K. And so this product is in K. And so by equality, this coset is also in K. So by definition of H, G inverse G prime is also in H. And so H is closed under left inversion. H is a subgroup. Finally, we need to actually prove that phi of H is equal to K. So what is phi of H? It's H mod N. What is that? Well, those are those cosets Gn, where G was an element in H. So those are those cosets where what's this definition? Well, those were those cosets Gn. Elements in H correspond to cosets in K. So you're looking at those cosets that are in K. Okay, so you're looking at K. So phi is surjective. Given a K, we see this was the appropriate H. Of course, this is not the only approach I could have chosen. The other approach would have been to actually just define the inverse function. And what would the inverse function have been? It would have been, well, we kind of see it here implicitly. Given a subgroup of the quotient group, you take exactly G such that Gn is in K. And I was using that definition here to prove surjectivity. You can actually use that to show that that's actually the inverse of phi, and then show phi composed of phi inverses the identity both ways. That's an alternative proof to showing surjectivity and injectivity. Note what I did not cover. is that there's another part of the fourth isomorphism theorem where you talk about normal subgroups. Here one would define NHG to be those subgroups K, where N is a subgroup of K, but K is a normal subgroup of G. And then, yes, it turns out there's a bijection. Here as well, given by the exact same map. The only thing you have to prove that's different is that H is a normal subgroup of G if and only if H mod N is normal in the quotient group. If you can prove that, then this automatically follows from what we just showed. Because then that tells you that if you restrict our function that we had from the collection of subgroups to the normal ones, if we restrict this function and we decide to restrict the domain to only normal subgroups, well, then we see that the codomain becomes the normal subgroups as well, because H being normal in G implies the quotient is normal. And the restriction of an injective function still ends up being injective, so this still ends up being an injective function. And then this reverse also ends up being true, because you say that, well, how do you know you get everything? Well, you take something over here. Because this is a subset here, you know it came from something. Because of this condition that tells you it had to have come from a normal subgroup. So it has to be a surjective map. So it comes down to this condition, which I'm not going to waste my time trying to show. It's also in the textbook.